that to see. It looks like there you are. They're all watching you. Turn that in. Okay. So I guess for those few that have not started the course yet, I encourage you not to put it off to the last minute. Probably a 1 week wouldn't be too bad, but not great, but wouldn't be too bad. If you start on Tuesday, your chances are really getting bad. But anyway, this time next week we'll be doing the first midterm here, and it'll go from the class time but longer. So, and the reasonable expectation would be that it might take you the class time. My goal is that if you're on top of stuff, it might take you the class time to finish, but it might well take you more. So I'm not, I don't have the habit of doing short exams, but so anyway, the idea is you'll have 2 hours. But this is next week, same time next week. Okay. Now, going around, it may go around numerous times. When this is here, there's homework that the grader returned it you gave it to me on last Thursday. The grader gave it to me on Friday, and then I kind of put it someplace, and I forgot to bring it Tuesday. And then there's a few that weren't picked up from the first time, so that's why I'm saying 2 of them. So there's a fat folder going around and a thin folder. The fat folder has a lot of homeworks, and the thin folder just has 1. And then I'm collecting these, and I'll collect them after class. And I will, I'm assuming the same thing's going to happen. So whatever you give me today, unless I screw up, I'm going to give you back on Tuesday, so you'll have all this stuff to study with for the exam on Thursday. So I should be returning everything to you Tuesday. Okay. Erasers somewhere. Surely. Here. Yeah, okay. I kind of want to get, my main topic for today is getting back to the chess problem and to discuss that more, and I'll be doing that mostly today. My plan is to talk about linear programming as viewed by a probabilist, which is one of the examples in the book, on Tuesday, which my general strategy is to talk about something that's on the topic. It's definitely in the chapter, but which you will not be critically responsible for on Tuesday. So you're actually today is the sort of the end of the material that you need to know for the exam, plus the homework, the fourth, all the homeworks. But so that I'm going to do something on Markov chains Tuesday that I'm not going to be really focusing on the exam. So the exam, this is sort of like today is up to today is the stuff that you're thinking about the exam. And given that you're following that 7-day warning, the advice is to make sure you know how to do the homework. The center of the course is the homework. And that's sort of, the new problems won't be the same, but they'll be close. So the homework is the main guide, rather than stuff in the text that we never talked about. The main thing you should focus on is the homework, and then the class stuff. Second, the class stuff. And the book should be supportive, but if there's some long example in the book that we didn't talk about at all, then you don't probably need to worry about it. So it's sort of more that you make sure you know the basics, don't spend 3/4 of your time studying things that we didn't cover. Unless you're really solid. Okay, I want to, I kind of oscillate from this behavior, which is, I'm sort of thinking it's non-productive a little bit, but every now and then I've tried to give you some sort of overview of how to think about the whole stuff, and I want to kind of go through this just a little bit at first, because I think I should do this. So I'm thinking first thing to think about is the state space. And this is kind of a point here that I'm making the point that the model is P. The model is the transition matrix P. And actually before that, of course, is the state space. So what should be the states is part of the thing, and then the P is, of course, depends on that. So that's actually included in P. You have to know what are the rows, what are the rows and columns represent. Those are the states. So what are the states is one of the issue. And a major issue is whether it's finite or infinite. And this case has the matrix P. So I'm sort of emphasizing the finite case because that's linear algebra in the usual sense, in the simple sense, the matrix sense is only going to apply to this. Because when the state space is finite, you're going to have a finite matrix P, and you're going to do all this linear algebra on MATLAB with a finite matrix. If the state space is infinite, you can also talk about a matrix P, but certainly you're not going to put it in MATLAB. Okay? So but Ross mostly operates here because actually the theory really holds for this. So it's not like the theory isn't true. I've just been emphasizing this because it's easier and I think good to think about this case first. But these two have slightly different. And this is a little bit, this is getting to mathematical fine points because once you go over here, there are weird things that have to do with infinity that you want to account for. Okay, so this is just emphasizing that as an issue. Then there's this business of classifying states and chains. So classify states, and we talked about this. So if we emphasize this, let's see, if I write this, I guess I'm recurrent and then transient, and then recurrent, positive recurrent, and then there's null recurrent, and then there's periodic, well, let's make it aperiodic and periodic. Could have that here too. But this sort of the nice case is going down here. The nice case where certainly both of these are pi equals pi p, but the interpretation is a little different in periodic and aperiodic as we discussed. Now, the point to keep in mind is now I'm actually focusing that the state space could be infinite, right? The state space could be infinite or could be finite. And then let's just kind of go through. This is in section 4.3 of Ross. So it's at the beginning, but I'm actually now discussing it from the point of view, well, the state space could be infinite or finite, so let's think about what that means. It's actually fairly simple. If we classify states, recurrent means that when you're in some state's recurrent if you're going to come back to that state eventually with probability 1. You're going to return. Recurrent means you're going to return for sure at some time. Not in one step, but some finite number of steps, maybe random, right? There may be no fixed, there may be no bound on how many steps it takes before you come back, but with probability 1, you will eventually return. So this means you will return. And transient means that there's some possibility you will not return. Now that actually simplifies, because if there is some probability that you won't return, in the long run, you will eventually, with probability 1, be gone. In the long run, you will not be there. If you start there, eventually you'll be gone. You'll only come back finitely often. It's kind of part of the theory, and it makes sense. A lot of this stuff you can prove. If you're thinking that you're going to be a mathematician, all these obvious things, you could say, how would I prove it? And you can, right? But that's not my focus. So I'm thinking that you could just, think that it's obvious to you. You read it in Ross, and you see it's obvious, but you know the classification because you know the story's different. So the absorbing chains tend to be in this category because we're thinking about you're going to eventually leave the transient states and you want to know something about it. So the absorbing chains are here and the pi equals pi p examples are over here. So this division is important. Now, here we have this other funny division, which has to do with the state space. This says you come back with probability 1. For sure, you come back. Here says that the expected time to come back, the expected number of steps to come back is finite, and here it's infinite. Now, if the state space is finite, this can't happen. If the state space is finite, the expected time to return, the expected number of steps to return is going to be finite. So you can't even have this case. This case only occurs in the infinite case. Now, the obvious thing that you should want is an example. And I mean, all the finite examples we did are here. So you want at least an example of this. So the obvious, what is an example of that? The obvious thing is the simple random walk. You're sitting someplace, and with probability of half, you go this way, and a probability of half, you go this way. And that's true everywhere this way and everywhere this way. So you start maybe at 0, and then 1, 2, and you just move back and forth. Now, it's actually complicated, and Ross has a discussion of this, and the math is complicated. You're moving around. Neither statement is obvious. If you do this, you could be drifting off and drifting here. So the math is kind of complicated, but the story is that you will return to 0 with probability 1, and you will visit any state infinitely often with probability 1. But the expected time to come back to 0 is infinite. Now, this is kind of weird, right? So you will return, but the expected time to do so is infinite. And okay, yeah.
The probabilities were different. Let's say it was like 4/5.
Yeah. Let's say it was p and 1 minus p, and p is not equals a half. Anything there, it's transient. If the p, let's say it's 1/3, 2/3. If anything like that, it's going to drift off here. It's going to be transient. Yeah, it could, the matrix, you could go, so this case is an infinite matrix, but it will be transient. So this is kind of thing, with probability 1, you will eventually drift. You can visit anywhere. You can visit any state. But eventually, you will go out here. And, that's like the strong law of large numbers. The law of large numbers is going to tell you that you will go out here. So whenever p is not a half, you will go whichever way p is biggest. Eventually, you will be gone from every state. You'll just go off to to infinity. If p is exactly a half, in this case, you actually you'll go arbitrarily everywhere, but you'll come back with probability 1, but the expected time to do so is infinite. So this all have to do with peculiarities with infinity, which is worth understanding, but is mostly second order here. I'm not emphasizing this, but Ross does. And now the interesting thing, this is the math problem. If the interesting thing is what happens when we do the same thing in higher dimensions. So in 2 dimensions, we could go 1 quarter, 1 quarter, 1 quarter, 1 quarter, 1 quarter. In other words, we do the same thing in 2 dimensions. And then you can do the same thing in 3 dimensions. Imagine, you're going on the lattice cube, and you go 1/8 to each of these directions. Interesting point is, the thing changes. So that in 1 and 2 dimensions, it's recurrent, but in 3 dimensions, it's not, which has to do with, the math of the situation. It's kind of complicated. And that's sort of interesting. And then you're thinking about what you're doing is, you're saying, you're actually finding an expression of what's the probability that I return and what's the expected time that I return, and you just compute those things and you could prove it. But this is kind of like you could go into this and you could spend a lot of time just on those problems. The simple random walk in 1 dimension, 2 dimensions, 3 dimensions, and in 1 and 2 it's recurrent, and in 3 and more it's transient, and then in all of them they're not positive recurrent. Of course, if we make the states, if we put some boundary, even if the boundary is at 10 to the 10 to the 10, it will be finite state space and everything will be positive recurrent. So it's kind of like, yeah, okay. So That is just to give an example of this. And as you do those different changes, those cases, it's interesting when P is not exactly balanced, you're in this case, and so forth. Okay. Okay, so actually, maybe the discussion now is, well, the state space could be infinite. We didn't talk about it. And then this was just as before, but you could have null recurrent, which is kind of like that comes up only in the infinite case. Now you have classifying the chain. Okay, and now you have it's irreducible or it's reducible. Now, if it's reducible, you can put it in canonical form. If it's irreducible, it's going to be a special case. And the canonical form, remember, has something like, let's say, here, you're going to end up with closed classes and open classes. If it's irreducible, there's only one class, one communication class. Here, there's a bunch of communication classes. If the chain is finite, so in the finite case, you're going to have this, and this zeros. You have the R, the Q, and then you have these blocks. So these are closed classes. These are recurrent states. Down here are the transient states. If the chain is finite, there has to be at least one of these recurrent classes. You're doing this reduction, and you're doing canonical form, and the canonical form says, put the closed classes up here. So in this picture, this set of states is one closed class, this is another, this is another. I have three closed classes. No matter what finite example I give you, there'll be at least one of these, because you have to end up somewhere. I mean, that's sort of obvious, right? There has to be one of these classes at least. And the standard examples that are complicated have two or three. But there has to be at least one. And there might be only, if it's absorbing, each of these has only got one state, and it's an identity matrix. But in the finite case, there has to be one of these. In the infinite case, there doesn't, right? In the example we just discussed, you take the simple random walk where you drift off to the right. There's only one class. You can get from everywhere to everywhere else, but you're eventually going to be transient. So once you make the state space infinite, you could have a single open class, and that could be the whole thing. So the situation, my point is just to kind of tie together, since up to now I've been acting like the state space is always finite. And Ross is talking about infinite. And so the thing I want to highlight for you is the differences, and that infinite kind of changes the story considerably if you allow it. So it could be irreducible in just one open class, meaning all transient states, or it could be reducible and have some funny collection of things. And in any case, you would probably do something like the canonical form, although its utility in terms of linear algebra gets less if these things are actually infinite. I mean, you're not going to be able to plug it into MATLAB easily. Okay. Okay, that, I guess, is the end of that. Okay. Does anybody have any comments? Or yeah.
Can you go over aperiodic versus periodic, like how to distinguish between the two easily?
Let's see. So how do you distinguish between them? Easily, I guess, is if you, so it's a little unclear how you distinguish between them easily. I guess you can see it easily if you think about it, usually. I guess so. If you raise it to a power, you just see that when you raise it to a high power, you just see that it's never getting all positive, right? And it's flipping back and forth. So you see it just by looking at powers easily. I mean, then you're getting to issues of math. So if you look at powers, you'll see that it's oscillating, right? So that if you think of maybe if it's, say, period 3, you sort of the states, if it was in nice form, it would look something like this, where you're starting here. So in one transition, you're always here. So this would be positive. The next, so P and P4 and P7 would always have this positive. So P, you go from here to here, one of these states. This is not 3 states, but a block of states, block of states, block of states, block of states. And I've arranged it so from these states, I always go to these states. From these states, I always go here, and from here, right? I've arranged it in a form where in one step I go from these states to these. And in the next step, I go from these to these, which is here. And the next, so these are the only positive entries in the matrix, right? So I could do a canonical form that says where can I go in one step, and then from each of this, and it would block like this. So this is the case of 3. I could be looking for this structure. Then, of course, when I raise it to high powers, I'll see that, you know, P, in this case, P to the 3K plus 1 will always have this form. But if I did P to the 3K plus 2, it would be positive here, right? It would be like this. And then from here, I'd be here, right? So that if I looked at P to the 3K plus 2, right? So I'm just saying, if you just looked at powers, you'd see it. Then you're getting at if maybe, which you could think about. You could think about how do I do this efficiently in an algorithm, which is maybe that you could actually address that, which I think is second order, not to worry about. I mean, given that you could just see it from raising it to powers, it's okay. But you could be more efficient. In all this stuff, if you wanted to identify all this structure, you could think about doing algorithms that efficiently do it for you. And that's certainly possible. But it's not so, I don't think it's so critical. Okay, right? I mean, your question might be in that direction. But you could say, what algorithm would I use to do this for me automatically? And surely you can do all of this stuff. But it's, okay, well, but I still open to questions. It's sort of like, I'm not sure if I was in the spirit of really wanting to hear your question. My answer wasn't in the spirit that I was listening, but anyway. That's just scratching your ear, not wanting to ask a question, right here. Yeah, okay. Okay, let's leave this. So, yeah, so what I want to do now is say, well, no, maybe I will put 1. And then, if I were, the reason for not doing that, I guess, is so I now have this graph, and the graph, the nodes are numbered, right? The nodes are numbered in the graph. And then on the arcs, or the edges of the graph, I put weights. I put them in boxes. If I had a different colored chalk, I'd use a different colored chalk, right? So the weights are here and here. So there's a weight on the arc between 1 and 2. So I have this graph. So I have 7 nodes, and I have a bunch of arcs. I could have it could be fully connected. I could have an arc between every pair of nodes, or I could just have arcs between some of the nodes. And what I'm going to do, this is continuing what we did last time, right? It's a little more abstract, but we have this graph. There's nodes, and there's arcs, and there's weights on the arcs. So I'm going to randomly move around on this graph. I'm going to make a random walk on the graph. And so I'm at some node, and I'm going to go to one of my neighboring nodes. And then from there, I'm going to go to one of my neighboring nodes. And each time I move, I'm going to randomly take a step. And I'm going to do so independently of the past. So that makes a Markov chain with a finite state. The state space is the 7 nodes. So if I make a P will be 7 by 7, the 7 nodes. And then let's say if we took the first row, 1, 1, 2, 3, 4, 5, 6, 7. We would see from 1 we can go to 2 or 3. We haven't said how yet. So now this is where the weights come in. Suppose when we're sitting at any node, we choose the neighbor to go to next with probability proportional to the weights. So if these weights are 7 and 2, we go here with probability 7/9 and here with probability 2/9. And then when we get here, we look here, we could go to 3 places. Some of the weights are 4. We go here with 2/4, here with 1/4, and here with 1/4. So we're just moving around, right? So we're moving around. So in this case, P1 goes to 2 with 7/9, and it goes to 3 with 2/9, and everywhere else is 0, and so forth. And you fill this. This is the model. We made the model. So if we thought of what I just said before, we'd say, in this example, the state space is finite, so any of that complication does not arise. The state space is finite. It's irreducible. You can get from every state to every other state, so there's only one class. And it's got to be closed. There's got to be at least one closed class. So this has got all the states are recurrent. The chain is irreducible. There's one closed class. Clearly, you're in this domain to solve this problem. So as last time, only thing to add to this is, say, some sort of efficiency about how to think about this even faster solution, right, for this problem. Okay, so I guess the story would be I would write then I'm done. Okay, this is the answer. What is the steady state? What is the long run proportion of times I visit node 1? I would write some of these weights from 1, and then I'm looking at 2, 7. So I'm looking at the weights 7, 2, 1, 1, 4, 2, 2, 1. So I've written all the weights on all the arcs here. This is the sum of the weights on all the arcs multiplied by 2. And I've put the sum of the weights out of 1. Well, first of all, is this going to add to 1? That's one test. It better be that if I do this for every node, it better add to 1. And you think, well, this is going to give me the sum of the arcs from 1, and then I'm going to get the sum of the arcs from 2. So for each arc, I'm going to count the weight twice, right? Because I'm going to look at the sum of the arcs from 1. I count this once. But when I look at 2, I'm going to count the same arc again. So each arc is counted exactly twice when I compute these probabilities, and that's what I put down here in the bottom, twice times the sum of all the weights. So you see that this has to be, these are probabilities. And you could check in this example that this is the right answer. Okay, now then, well, that's this example, but I mean it's beginning to be clear. So if we did Markov mouse, it would look like this. This is Markov mouse. This is irritating. Okay, Markov mouse, right? I'm now making the rooms nodes. Rooms are nodes. This is room 1 up here. And the doorway, the paths, so the rooms, I've changed the form of Markov. This is not, I've made this room 1, I've mapped that into this, right? I'm representing the 9 rooms as the 9 nodes, and the doors are the arcs. So I fit Markov mouse into this framework, right? same way. So this is the 9 rooms, and then I actually just put weight 1 here. I don't even need the different weights. So here I would see, how many Markov mouse, I would see there's 2 out of here, so I would get pi 1 is 2, and then how many numbers are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Wait, I did 1, 2, I don't have this one here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Right? And then I've got to wait. I got 12 times 2, right? So so this room is 1/12. I guess that's the right answer. Right? Same thing. So I've represented this problem as this graph, so it's the same problem. Yeah?
Why is it 2 times 12? Because aren't some of the nodes, aren't the rooms kind of more than twice? Like if you look at
Well, so think now, here's the room and here's the room. So this arc is counted as a arc out of this node and this node. So each arc connects exactly 2 nodes. So I count this arc once from node 1 and once from node 2. So from node 1 I count these 2, but then when I add up all of them, I'm going to count the 12 twice. And I'm going to have 9. I'm going to get that I'm more likely to be in this 5 is going to have, because there's a lot of stuff from 5, I'm going to get that I'm more likely to be in 5 as we would. So this will agree with what we did before. This means that we could have made this mouse maze humongously big, right? Like the chessboard, and bigger and multi-dimensions. We could solve it without any more difficulty, right? Could solve any of the, if I'd given you a mouse maze with 3 million rooms, well, we could have solved it the same way, which is then it gets a little more challenging. So this case, remember, was periodic. Right? This was period 2 because there was stuff the odds and evens. This thing, I think, is aperiodic because it's got different kind of structure in here, but you have to think about it a little bit. The issue about whether it's periodic or not is a little complicated. You might think if it was just this, it would be period 3, but if it was just this, was period 2. So when you do them together, it's going to be period 1, but you can check it. So it's not periodic, but this is periodic. So the issue of whether it's periodic or not is not so clear. So the question about just looking at it, what's the period of the thing, is not so obvious. And you could indeed want to say, well, I want an algorithm that says, boom, plug the thing in the algorithm and it's going to tell me what the period is. And you could do that, but I'm not emphasizing that. So if it is periodic, when you solve pi equals pi p, you're getting the long run average frequency that you're there, but the long run's going to oscillate. Okay, so still you're going to have this. Both the periodic and the aperiodic case, you're going to do this. Okay, so, and then to repeat, let's say, if I were to ask, if this was the return time, where, what is the expected number of steps by the return? What's the expected time that I return to 1? I start in 1, and what's the time to come back? This is this. Right? So if I want to know the expected time to go from 1 to 1, or if I write this way, this is the time to go from 1 to 1. Number of steps is 1 over the steady state probability. So if I ask all of the night, if I start here, what's the expected number of steps before I return? That's this, and this is then the solution coming from the solution of this. So the missing part, there's only one missing part. The neat thing is why is that the right answer? It's actually enough. Part of the story is that it is the right answer, and you could check it, and therefore it just turns out it's nice. But there's actually a nice theory that applies to a lot of problems that's very important, and it'll be very important in the continuous time problems we look at later. So the question that I want to talk about, this is sort of so far as repeating what we did last time. The question now and the why, the answer I'm looking for, this is different from, I'm thinking the why is important as opposed to proving. I'm not emphasizing, my point is not to emphasize proving that it's correct, but why it's correct. Meaning that I'm thinking that there's some substantive ideas worth knowing about why it's correct, which is different from technically proving something that's obvious to you. I'm thinking, the point is I'm claiming I'm going to tell you something that's not obvious and that improves your understanding, not that it's a mathematical technicality, right? Okay, that why doesn't mean prove it. It means there's some explanation. Okay, and okay. So this is our kind of problem. But of course, the general problem has some finite number of nodes and some arbitrary weights on them, right? And if the graph better be connected, right? You better be able to get from every node to every other node in order for it to be one closed class. So you can see from the graph that you have to be able to go from every node to every other node, otherwise it's going to be reducible. Right? I mean, if you made the example look like this, and then over here is this. I mean, this is one example, and this is a separate one. And if you start here, you're never going to get over here. And if you start, right? So I'm assuming that you can get to all of them. So we have this thing like this picture here. But in general, you could have, we have 7 nodes with weights on the arcs. Could have any number of nodes, any number of arcs, any kind of weights, and the answer. So what is the answer? The answer for pi 1 is the sum of the weights, so any I. This is the steady state probability of being at node I is the sum of the weights out of I divided by the sum of the weights out of k summed on k. Right? This is what I'm claiming. The probability should be the sum of the weights out of I divided by the sum of the weights, which is, this is bottom part, is the same as the sum of all the weights times 2. Somehow I've got all these weights. I've got to be careful here where, let's say, I don't count things twice, right? So I don't count, if I don't count them twice, I'm going to multiply by 2. And whereas here, I'm going to guaranteed to count them twice because I'm going to look at all nodes and sum the weights from the nodes. So I count them only once. Here, I sum all the weights, but I don't count them twice, so I multiply by 2. So the claim is that that's believable. So then you say, well, okay, fine, that's the answer. Okay, so then the question is, why is that the distribution? So, so the point, so what am I doing? I'm about to fall off the thing here, right? But what's my point here? I'm just crazy, right? Okay, well, what the hell am I? Okay, why? Okay, the point is here that you want to go backwards, okay? If you go backwards, there's something special about going backwards. And so that's what we want to look at. So we want to look at going backwards, and unlike me, sometimes when you go backwards, you look the same as when you're going forwards, okay? That's going to be crucial. So, we're coming to this. It's reverse time. So go backwards. Reverse time is go backwards, okay? And then reversibility is when you go backwards, it's the same as going forwards, which is kind of unlike people. We don't look that way. Okay, now let's consider that. Okay, we could consider that here. Here's plenty of room to consider that. We're going to go backwards. So what we want to do is define a Markov chain going backwards. So we're going to think of a Markov chain going backwards. So you're going to say, where did I come from? Imagine you fundamentally go forward, but you're asking, if I'm somewhere, where did I come from the last step? So you're going to define a Markov chain you're going to try to do this, to be the probability that xn is j, given that xn plus 1 is equal to I. I'm going to look at the probability, the qij, this transition from I to j, is going to be, and actually this would depend on n plus 1. I don't know where to put that. Because it's not n step. This is one step. So I want to do this. And I want it to be Markov. So if I'm going backwards, I guess I want to say this. So I'm actually going to want that to be so I want all this to be true. I want that to be true. I'm asking, my transition probability is, now I'm going from, when I go from I to j, I'm really saying, well, here I am at some time m plus 1. I'm conditioning on I. What's the probability that I came from j? Given that I'm in I came from j. That's my proposed transition probability. And I want it to have the Markov property, which is going to be that if I condition on the future, it's not going to matter here. So going backwards, it's going to have the Markov property. Let me see. I guess I want to use this. So let's think about that. Now, the thing to say here is, I've just set this down, and the idea is clear before I start crunching. The thing to say is I'm just writing a bunch of conditional probabilities. So when you want to see what happens, all you do is apply the definition of conditional probability. I mean, it may look, there's nothing magical in the steps you're going to do. You're going to apply the definition of conditional probability. So if you think of doing this, you're going to write what that is. You're going to write probability xn equals j, and xn plus 1 equals I, and xn plus 2 equals I n plus 2, and then some stuff, and I'll leave that there, divided by the probability that now the xn plus 1 equals I, xn plus 2 equals I n plus 2, and so forth. Because I'm writing, by definition, the probability, this conditional probability is the probability of both of these things divided by this probability, just by definition. So that's just this. And this, now, if I rewrite these things in terms of what I really know, I have a p. So I could write it this way. Right? So this is the probability of being in J to start with, which I don't have any control over. And then I have to go to I in the next step. So that's this. And then I have to, in the next step, go here, given that we're in I. So I'm just rewriting it in terms of this initial thing, the transition matrix, and this. And down here, I have to do this. I'm going to do the same thing. I'm going to write this as the probability that xn equals j. And then I'm going to have p ji, and then I'm going to have the probability that xn plus 2 equals I to the n plus 2, blah, blah, blah. Xn plus 1 equals I. And then down here, I have to sum on j. Because I'm not at any particular j. I'm just sticking in, I'm in some j, and then I move from j to I, and then I do this. So I'm just rewriting that in terms of my current stuff, in terms of the matrix P. I'm sticking the matrix P in here whenever I know it. And I have the other stuff. And all I'm doing is using the definition of conditional probability. So it's nothing, I'm not doing anything really tricky. Now, the thing to observe, well, this is a sum on j here. So these terms are being added up. So it's a little complicated where the j appears. It's a sum on J. But there is no J here. There is no J. This factor's outside the sum and can be canceled. There is no J here. This is I. There's no J here. So this stuff goes away. That's showing you that this is the true. This extra garbage goes away. That this really has the Markov property going backwards. That's what that's showing. So then you're sitting here looking at this. So that is just this rewritten. Once I've gotten rid of this extra stuff, I've written this down. This thing over here, what's left, is a direct expression for this. So this first step is just to show, going backwards, I have the Markov property. But there is a problem still. And the problem is, here I am, and I have this probability of being in J at stage n. And it sits in here, and it sits in here, and I don't know what it is. So this probability is, this is well defined. I can make this the definition, that I'm going backwards. And I see that I get this Markov property. So I've gotten to here. And this is the probability xn equals j pji divided by the sum on j of probability xn equals j pji. This thing equals this by what I just did. But this probability here is complicated. It actually depends on n in general, right? Because it's the probability at stage n I'm in J. So an important thing here is this isn't actually so nice as it seems. This isn't so nice because this depends on n. And therefore, this probability, if I do this backwards, really depends on what stage I'm at. This transition probability is not independent of n. And we really want a Markov chain where the transition probability is independent of n. So how can we make this independent of n? I mean, what would we do? Well, we're going to need to assume something, because in general it would not be independent of n. So what would be the obvious thing to assume in order to make this independent of n? Somebody volunteer. Yeah. Yeah, let n go to infinity. Think of it as stationary. If it's stationary, if the Markov chain were stationary to begin with, if we had let n go to infinity, so we're in the steady state. If we were in steady state to begin with, this would be pi j, and then pji over the sum of pi j pji. If we started in stationary. And that's the standard definition. Then this is well defined. This is well defined. So whenever the important point, let me get rid of this garbage, the math. But the math is just conditional expectation. The point is qij equals, by definition, pi j pi ji over the sum on j pi j pi ji. This, by definition, if I start with a stationary Markov chain with steady state vector pi, this will be a reverse time Markov chain with a q, this transition matrix that's independent of n, right? If I made that assumption. So if I assume that I have an irreducible recurrent Markov chain with pi equals pi p, under this condition, there is a solution to this, and if I've got the pi, and that's where I am, I'm operating in steady state with pi, if I assume that, then when I do this construction, this probability of being in J is pi j. So if I assume, in addition, the important point is, in order to apply this reverse chain stuff and really get a nice clean Markov chain, I need to assume I've got an irreducible recurrent Markov chain, so I've got a pi for pi equals pi p. And I'm operating in steady state with that pi. I've got a stationary Markov chain, so whenever I look at time n, if I look at this without any conditioning, the probability at time n of being in J is just pi j. And I assume that. If I assume that, then this becomes the definition, and I've got a bona fide reverse time Markov chain. So this point, what I'm trying to do here is say, if I look backwards, and if I have a pi to go with pi equals pi p, then I can always define a reverse time chain. And this is the transition matrix. So that means if you have a stationary Markov chain, you could always look backwards as another Markov chain. Kind of a useful insight. You can always do that if you want to think backwards. Okay? That doesn't sound so great. It's not so great. It's sort of vaguely interesting. The next step is the interesting part. That's interesting. A mindset is good. You could go backwards under some conditions. Now we come to reversibility. We haven't got there yet. But reversibility is obvious. This is the reverse chain. There is one that goes with a stationary pi. You know, you've got p and you've got pi. These are given. This is the Q is the transition matrix of the reverse chain that goes with pi and p. And here it's defined. This is the transition matrix of the reverse time Markov chain. You need to investigate whether this chain has its own solution, alpha q equals alpha or something, right? I mean, but this is a Markov chain. We're not saying anything about that. However, now, what would reversibility mean? Now it's sort of, the next step is important, but it's obvious. What could reversibility mean here? The reversibility, the obvious thing is, it looks the same going forward and backwards, means that this reverse time chain could be the original one. And that's what reversibility is. So the reversibility is if Q equals P, then time reversible, or just reversible. So that, let's just focus in on that. So this first part is actually setting the stage and is complicated, but this last part begins to get, once you put the two pieces together, it gets very simple. So you're now saying, I want this to be true. Wait, I didn't do this right. Well, it's okay. It's okay. I didn't do this right, though. I didn't do this the way I wanted to. So let me. This is all correct, but I want to observe that things are actually simpler still. By pi equals pi p, this thing on the bottom is an instance, one state of pi equals pi p. I'm looking at the equation pi equals pi p. When I look at pi p, this will be pi I. So this actually is simpler. Let me just, this what I wrote down is correct, but I simplify this. Yeah. The bottom, I'm really sure. Yeah, you're thinking of it. This J is summing, but this is fixed. Well, no, this is okay. There's nothing wrong with this because this J doesn't refer to this. You could make it K, but it could be, there's nothing wrong with what's written there. No, but that's nothing wrong with that. You can have one somewhat, you know, this is easier to look at. But the other one's totally right too, but this is okay. And the point is, well, this was that step we got here. If we do one more step, we get here, so it's simpler. This is just, again, this is not reversible. This is just expressing this reverse chain. You need the pi, you need the p, and then you get q. Right? Given the stationary chain, you're going to get the reverse chain, and it has a simpler transition matrix. But if they're equal, that's just this. If it's reversible. This is just to say if q is p, then it's this, which can be rewritten this way. Now, actually, the kind of standard thing you do is you forget all this stuff that leads to here, this is kind of the derivation. You just remember this. You're in steady state with pi. You're thinking reversible. So this is saying, well, this is, if you will, the flow from I to j. The probability of being in I, and this is the probability that there's a transition from I to j at any time. I'm in I, and the next time I'm going to go to j. So what's the probability that I'm in I, and what's the probability of this pair at any two states, that I'm in I and I next will be in j? And that turns out it's got to be the probability of the same thing in the reverse direction. Probability of being in I, ij in two steps, and ji in any two steps. And they should be equal for all pairs. So clearly, if your structure looks like this, if your state space looks like, well, this is, what am I trying to say? If it looks like, I guess, if you have some states, right? If you can go from 1 to 2, but you can't go from 2 to 1, you're going to be in trouble satisfying this. I mean, you've got to both be able to go in both directions. That's not this picture. It's just any state. If you pick some state you're in, well, that's like this picture. If you're in one node and you can go to some other node, you better be able to go back. That's a kind of minimum requirement, because you can't have this unless they're both positive at the same time.
Where you can go back?
Well, so in this picture, if I'm in any node, and you think of I'm in node 1, I can go to node 2, or I could go to node 3 next in one step. So I better from 2 and 3 be able to get to 1 in one step in order to have this, because I have to have the probability of going the ij order, going from I'm in 1 and then I'm in 2, has going to somehow be the same as being in 2 and then going to 1. And so as a minimum requirement, if I can get from 1 to 2, I better be able to get from 2 to 1. Yeah.
Even though those probabilities might be different.
I'm saying these could, yeah, because these would be different. That's right. So this is saying one thing that's, you can't, this has got a bunch of conditions, right? There's 4 unknowns here. These 4 elements are all different. But if one of these is 0, the other better be 0. So I'm just drawing an inference without knowing this. There's 4 things here. These cannot, if one's 0, the other has to be 0 without knowing any more. I'm assuming these are not 0. So if one of these is 0, the other is 0, without knowing all 4. I'm inferring that if I can go from 1 to 2, I better be able to go back the other way, which is true in this example. That's not the full requirement, that's just a necessary condition. So you say, well, I'm not going to have reversibility if I can't go both directions. Yeah, so the state would be if you went from here to here and here to here. If you go from 1 to 2 to 3, you're in some cycle, and you go in this order. I can go from, that's this picture. If I can go from 1 to 2, 2 to 3, 3 to 1, it's fine. But I go to 1 to 2, I can't go back. It can't be reversible, right? Anytime you'd have a cycle of length 3, you can go from 1 to 2, 2 to 3, 3 to 1, but you can't go back to 2 to 1. So it can't be, yeah.
So there's a difference between saying you can construct a reverse time Markov chain and then saying the chain is time reversible?
Yeah, very different. So I'm saying, the first part is saying, well, you think, first remember, I started by saying, let's just suppose we go backwards, which you can do in any case. When you first start to go backwards, you find that you can't make a Markov chain with a transition probability independent of the transition unless you make it stationary. So all I need to do to get this is I need to assume that I've got a stationary chain, right? And then I've got a reverse chain. But the reverse chain is therefore true very generally. For any stationary Markov chain, I've got a reverse chain. The time reversibility is a very strong extra property. In general, Q will not equal P. Very greatly, in all these stationary cases, you can do this. But it will usually be that Q is not P. The good thing is that for a whole lot of problems, very interesting operations research problems, Q does equal P, like this graph. And when Q equals P, you're really in business. That's the point. And it often happens. And when you know that, things are fantastic. And then the story gets fantastically easy. So the story already at this level becomes easy. And that's going to give you the answer to this thing easily. Once you realize its reversibility, everything, what you need to prove is easy. So let's look here at this thing a little bit. So I was just making, you'd say, well, one of the things your point was, well, is reverse time automatically time reversible? The example where you move this way among 3 states is showing I can go from 1 to 2, but not 2 to 1. Nothing like this could be reversible, time reversible. So just anything like that in your diagram of flow of states would be not reversible. So you have to be able to somehow go this too, right? Then if you move this way, like in the graph, you can move back and forth. Okay. But beyond that, you need this to be true for all pairs, for all I and j. You need this, right? You need this for all states. Now we come to the why is this good? I guess, yeah, this is a critical point right here. Now, see if I can make this transition right. It's not just that if things turn out to be good, it's not clear where you've gotten anything good out of this yet, but this is the thing this is called local balance. So this characterizes a reverse time chain. If the chain is reversible if and only if this is true. But more is true. This is what you want to compare is to this. Here's this, and here's this. Now, the point is, in general, when you want to find pi, you solve a system of n equations and n unknowns. N equations, n simultaneous equations. State space might have 1 million states. You solve a system of 1 million equations and 1 million unknowns. Could be tough, even for MATLAB. Okay, now here, how many equations do we have here? We have a lot of equations, right? N squared equations, right? Well, this is n equations. Here's n squared equations. However, there's a big difference. Here we have 1 equation to solve. Right? You have to solve 1 equation at a time in this thing. You can look at this one and solve it by itself. 1 equation to solve by itself. This thing. I mean, you're going to end up solving them all, but they can be separate. They all got to satisfy this, but it's got this thing. So the point is this is easier to solve than that. But moreover, if you solve this is the part that's not entirely obvious, but is perhaps clear, is if this is true, it's going to turn out that pi is a solution of pi equals pi p. Everything good's going to happen. So that not only is, if there's a pi, if there's a p and a pi, and if q equals p, and so forth, you have all this, but it goes the other way. If you can find this, if you can find a pi that satisfies this, it's going to satisfy pi equals pi p, and so this is all you need to check, not this. That's the good news. You check this. So all you need to do is check the flow from each pair of states. So you now just focus on 2 states and do this. And the standard thing, the standard approach, and actually I don't know you can improve on this much, is the standard approach is you guess pi. Sounds, but this is not too easy here. But here it's going to be easy. You guess pi and pick 2 states and check it. You're done. You guess pi, pick 2 states and check it. So you don't do this. You don't ever solve a system of n equations. You solve 1 equation, and you guess the pi and check it works. Yeah, and a lot of people have worried about, there is a story about, well, how do you guess right, and so forth. That's not actually too great, the story about how you do better than guess is a little weak, but you mostly get better at guessing. But there's a lot of books on this. It's not so, that answer might be kind of feeble, but it's actually kind of a lot. You have to do a lot of work before you get beyond that. Yeah.
Pi and pi j, or just
Yeah, so in fact, you're going to guess the whole form of pi. You're going to guess the solution, pi I and pi j. So in particular, you're going to guess the thing you're going to guess the whole vector pi. Pi is going to have some simple structure, and you're going to guess it has that structure like we did here. We had a pi. I wrote the pi down. So once I've written that pi down for this random graph, all I do is just check this, and it's a simple calculation. Yeah.
Yes, pi, you can just check it with the other equation as well. Just
Yeah.
multiply by p to see you get a pi back.
Yeah, that's not quite so easy, though. You now have to, yeah, that's true. It's a little harder, though. So, yeah.
Versus checking for every pair of ij.
Well, you do it in general. So this ij is actually going to be once. You don't do it n squared times. You do it once because you have the pi for each one. So you actually do this. You do this calculation twice. You don't sum anything, and the sum might this pi p might be a little bit involved. It's not so involved, but this is a matrix, a vector and a matrix which may be humongous. Whereas this, in fact, is going to have a simple, you're going to calculate this once, really, for any two states. You're going to calculate this, and you'll calculate that, and you'll check it. You'll see it's now, there's an important fact, though, that must be here. The point is, if this equation holds for all ij, then this holds. That's key to what I'm saying, right? So you'll see that it's simpler because if this holds, then this holds, but not the reverse. Not the reverse. In other words, you can have this without this. You can have pi without it being reversible. But if this holds necessarily. And then all you do is sum this up and see that that's this. If this is true, then this is true. And you can start by, you can say, let's look at that. Well, okay. Let me just say that because we're running out of time. If you sum this, so if you say, well, pi I pij equals pi j pji, this is true, then you say, well, I sum on I, both sides. Then I do this by pi equals pi p, this is pi j. And now I'm summing on I, and this is j, so this just comes 1, pi j. Right, because this goes outside. I'm summing on I, and it's just the sum of pji, that's the row sum of the matrix, is 1. So this is this. So when you just take this equation and sum over one of the coordinates, you get 1. You get this. You see that this is true. Or am I saying that right? If you sum this, you get now, maybe I'm not saying this right. If I sum this, I've got, if I sum this on I, I've got, if I sum this on I, if I sum on I, I've got pi j. And if I sum this on I, so let's see. If I sum on I, this is pi p. I'm saying this in another way. If I sum on I, this is pi p. And if I sum on I, this is pi. So pi I and, see, pi p of j. And if I sum on I, this is j. I'm not saying this right. If I take this equation and sum on I and interpret it, when I sum on I here, that is by definition pi p evaluated at j. So if I sum on I, that's the meaning of this, which is going to be pi j, because pi is equal to pi p. But if I just sum on I, that's the definition of pi p evaluated at j. And if I sum on I here, this goes away, and this is pi j. Simple thought, if I sum on one of these coordinates, the equation becomes this one. So this overall coordinates is this summed up. So then, it's a little bit, it's true that you can just check here, too. But when you get these problems, this is going to be a lot easier. I mean, you get these big, complicated problems. This calculation, actually, in fact, you're right. So when people solved a lot of these original problems like queuing networks, there's something called a Jackson queuing network. He solved that by guessing pi, and the original method was he guessed pi and checked pi equals pi p. Complicated queuing network. Guessed pi has some special structure. Do this, just what you said. That would be what you'd do. It's totally straightforward. You know all you need to do is find pi, you guess pi, and you solve it. Okay? And I guess part of the story, maybe the story is a little bit explanation, but this is even faster. Not much. It's a little, the calculation is not a whole lot different, but it's faster.
Do you have to know the entire effect of pi in order to solve pi I?
Yeah, so you're in
pi I and pi j?
Yeah, you actually want to know a general form. So here, I wrote down, now, the thing you should do for yourself is here, in this example, we wrote down the general form in the general case without any specifics of the weights and so forth. You'll see this in the book. All you do is just plug that into here, and there's no summation. It's very simple in this case. It's not too much more difficult to do this, I'll have to admit, but a little bit.
This makes it easier for this pi? The local balance.
Yeah, and so you're thinking about this. Once you know this structure, it's maybe you're thinking, what model is it going to have this structure? You can see this. This is not only solving this. This is telling you it's reversible. The reversible is going to have this nice structure. You're going to know that nice stuff is going to happen. It's a little bit complicated to sort out all of it, but then here you're seeing that in the simple story in there, that answer just follows into this very naturally. And part of the reason the answer is simple is because it's in this structure. So it's a little, maybe I'm overemphasizing this step as being instead of this one, but the simplicity has to do a lot with this. Well, actually in this, let me, a thought of reassurance. My class today, the stuff is all in section 4.8 of Ross, and he says the same thing in a different way, so you can read it there, and it'll be said differently, so you can, the two together ought to be sufficient. And it's only like 4 or 5 pages long. So it's there. It's not, unlike some of the lectures, this is really very close to the book. So you can compare to, one of the two ought to make it clear. Okay. Next time, we're going to do linear programming from a probabilistic view.